Hey guys, this is the last video of Unit 5 on bonding. This is 5.7, dealing with intermolecular forces. Now, notice you have two practice sheets that go along with IMFs. They are always on the Regents exam, so I really want to make sure that you guys understand them. And really it comes down to you've got to know what they mean. So flashcards are going to be your best friend as you're studying. Know really their definition. So if you understand that, it'll make it a whole lot easier for you. So let's jump right in. We're going to be on page 24. So here we go. So intermolecular forces, aka IMFs, you'll see me write that a lot as I've already done, as well as on practice sheets you'll see IMFs. Remember, these are only in covalent molecules, never in ionic compounds. I would encourage you guys to highlight that, star that. That's kind of the very first place to think about, as well as polarity, right? Ionic compounds are always polar because they have their charges, where covalent have polar versus nonpolar molecules. So the last two videos have really just been focused on covalent molecules, not ionic. Okay, so that's kind of the first place to start. Now, the other piece with intermolecular forces where people get confused is that these are weak forces that occur between molecules, okay? And that's the key, is between. They hold the molecules together. So the way you want to think about it is that they are not like bonds. So we'll get more into that here in just a second. These IMFs only exist in the gas phase and liquid phases. Now when we do kind of our KMT unit, kinetic molecular theory, later on in the year, and we discuss all the phases of matter in detail, we'll kind of come back and touch on these intermolecular forces even more, so they're not going to go away. So really know your definitions now. We'll apply these forces more later on in the year. They're called weak forces because they're much weaker than chemical bonds. So these are not chemical bonds, okay? IMFs occur between molecules. Bonding occurs within molecules. That's the key. You've got to know this and be able to distinguish between this in your mind, so find a way that works for you. One of the analogies that I use is like an interstate highway. Okay, so if you think about like interstate, I know you guys don't really drive yet, but as you're driving, you know, if you want to get from, say, Buffalo to Rochester, the easiest way is to go on I-90. Well, I-90 doesn't just stay within New York State. It goes, you know, for hundreds and hundreds of miles. It goes through Pennsylvania and Ohio and like Indiana and Illinois, and it just keeps going. So those interstate highways are highways that link different states together. And that's kind of what's happening here with these intermolecular forces. They're linking molecules to one another. So you can see here, we've got one molecule of HCl and we have another one. The intermolecular force is what's keeping those together or kind of close to each other. Okay, whereas a bond is holding atoms together. So it's holding the hydrogen atom to the chlorine atom here. Okay, so a bond is much, much stronger. Intermolecular forces are weak that are holding molecules to one another. So this is going to be a great picture to kind of hopefully help drive that home. So again, find the way that works for you. You've got to know what the difference between a bond is, where you have a sharing of electrons, whereas an intermolecular force is just like an attraction. Okay, it's just holding, it's just keeping the two molecules together in the same vicinity after electrons have already been shared between atoms. Okay, so really study this stuff and make sure you know within it. So just to remember, IMFs are not bonds, they're weaker. So what I've got down here at the bottom of page 24 is kind of like a little diagram. This is going to help you guys kind of keep the bonds together in terms of strength and then kind of compare it to intermolecular forces. So over here, on the left side, these are the strongest forces. So ionic compounds are greater than molecular compounds. Sorry about that. Just remember though, guys, there is one exception: network solids. Network solids are the strongest, and that's a covalently bonded substance. The two big ones that you're going to see on the Regents are diamond and silicon dioxide. Okay, those are the two big ones. They are stronger than ionic compounds. But for the most part, ionic compounds are the strongest because of that transfer of electrons. And then molecular compounds or covalent compounds that sharing, they're weaker than ionic, but they are still much, much, much stronger than all your intermolecular forces. So if you look over here, intermolecular forces are very weak. Hydrogen bonding, even though it says bonding in it, is not actual bonding. There's no sharing of electrons or transfer of electrons that's taking place. It's an attraction. And we'll talk about what that means here in just a minute. Dipole-dipole falls in the middle. It's the medium strength intermolecular force. And then dispersion forces, they're called London, and we'll get to this in just a second, London dispersion forces or van der Waals forces. They're the weakest, okay? So this is going to be kind of a good thing. Hopefully maybe make a flashcard or two to kind of help you with this, just to kind of put it in comparison. You might be thinking, well, why are network solids greater? And I don't know if I've touched on this in detail earlier. It deals with how they come together, how they're bonded, not in terms of sharing, but just kind of the arrangement of their atoms. Okay, so diamonds have a very unique structure to them that gives them such a strong bonding characteristic. If you have more questions about it, ask me in person and we can kind of discuss it more. Since we're talking about strength here, I kind of want to just briefly mention, this has nothing to really do with, it's kind of a little aside, has nothing to do with intermolecular forces here, guys. Just, double, single, and triple bonds is really what I want to kind of talk about for just a second. So in terms of strength of bonding, okay, you've got triple, you've got double, and this should be pretty obvious. Oops, I can't spell today. And then single, okay? Guys, hopefully it goes without saying, triple are going to be your strongest held together, and then single are going to be your weakest bonds. Okay, just think about like a rope, one rope versus like two intertwined versus three. It's like almost impossible to break. So triple bonds are the strongest, and then single bonds are the weakest. I kind of forgot to talk about it earlier when we talked about single, double, and triple, so I want to kind of just hit it now. And then length of bonds. Okay, in terms of longest to shortest, okay, well, think about it like this. Which do you think is going to be longer or shorter? If something's weaker, okay, is that going to be closer together, kind of more tight-knit, or is it going to be kind of further apart? It's easier to break it apart a little bit more. Think about like a long-distance relationship versus like one that you're close to and you see somebody every day. It's probably a stronger relationship if you're closer together. So longest are actually going to be a single bond. Okay, they are going to be longer than double. Notice double is always in the middle. And then triple is going to be your shortest. It's going to be the closest together. So just kind of note this. You can kind of put this back with, bonds in general. But since we're talking about relative strength, I just wanted to kind of go over it really quick just to make sure you guys had that information for future questions later down the road. Okay, so just remember though, these intermolecular forces we're about to get into, kind of go over all their definitions, they are not bonds, they are just kind of attractions between molecules, okay, and there's your good picture for that. So let's talk about the three types, okay. London dispersion forces, LDFs, or van der Waals, they mean the same thing, okay. These are synonyms that mean the same thing, all right. These guys are the weakest. They are the weakest of all the intermolecular forces. So I'm going to put weak right here. And we're going to see as we go down this chart, we get stronger toward the bottom. Okay? But these are weak. Every single molecule has dispersion forces. Okay? They are only important for nonpolar ones. So as you go through and you're going to be asked questions about intermolecular forces, you need to, one, draw the structure out, identify is it ionic or covalent. Okay? That kind of determines the bonding. If it's covalent, you're going to be asked some questions like, is it polar, is it nonpolar? And then from there, determining if it's polar or nonpolar, you can identify what type of intermolecular force it has. Okay, so lots and lots of practice with this. Don't shy on the practice. If you have questions or when you have questions, ask. Ask a neighbor, ask me, so that you can really get this down. So London dispersion, if it's a nonpolar molecule, you know it's going to be London dispersion or van der Waals. Again, same thing, same name for that. The more electrons that you have in a molecule, okay, the greater or stronger the LDFs. Okay, so the more electrons, the greater those forces are going to be. So kind of the bigger the molecule, the stronger those London dispersion forces are going to be. This is based on the electron-electron repulsion creating brief dipoles. Okay, very, very brief. And we'll talk about dipoles more in just a second. Within the atoms / molecules, okay? It's not dipotes, it's supposed to be dipoles. Okay, so again, these are the weakest. They are only with nonpolar molecules. The more the electrons, so the bigger the substance is, or the structure of the molecule, the greater these forces are going to be. So the smaller something is, then it's going to be weaker. All right, the next one are dipole forces, or dipole-dipole. These are in molecules something like such as HCl, where you have both positive and negative ends. So again, looking at your structure is going to be the first place to start. Draw the structure out. Don't be too lazy to do that. It doesn't take more than like 20-30 seconds to draw a structure at this point. And then you can kind of see, is there an equal or unequal sharing? Which one has more electronegativity? There's my partial negative and partial positive. So these are going to be within polar molecules. Okay. And that's what creates that term dipole, two poles. Okay, that's what dipole equals. This results again from that unequal or asymmetrical sharing that takes place. Sharing of electrons. So again, dipole-dipole equals two molecules with permanent dipoles, and they're attracted to one another, okay, temporarily. Again, these are not like bonds where it's kind of permanent, where you've had that transfer, that sharing of electrons. It's permanent. It's not going to change it unless some other chemistry happens. Here, these are temporary forces of attraction. Now remember, up here, okay, in the in the London dispersion forces, they're brief dipoles, okay? Very, 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 very brief. Here, these are permanent dipoles, so they're going to be temporarily attracted. So you have this thing called a dipole moment, which is the measure of the strength of the dipole within a molecule. So basically, how polar is it? Okay, that's what this means. Okay, dipole moment just means the longer the dipole moment, the stronger the polarity. The shorter it is, the less polarity it's got. Okay, now again, what it all comes down to is electronegativity. So the greater the difference in electronegativity between the atoms, the greater the polarity. Again, this shouldn't be anything super kind of new to us. We're just kind of putting it in paper, but the greater the difference, the more polar it is. Okay, polarity / dipole moment. So remember, don't get confused with all the terminology. You're going to have to study this. Okay, this can be confusing. There's a lot of information here, so you've got to make sure you read over your notes. Make flashcards for each type of force, for each type of bond. Make sure you really know what's going on within it, and that's what the questions are going to try to do. Since this is so conceptual, meaning lots and lots of terms, this is where people can struggle on the regents. They can twist or change one little word, so make sure you're reading things carefully, that you're taking your time, and that you really know the concepts. Okay? So the higher the dipole moment, the stronger the IMF. So dipole moment just means the greatest difference in electronegativity. So the greater the difference, the stronger the force. Okay, so the stronger the force is, the intermolecular force, the higher the melting point is going to be, and the higher the boiling point. Now, we're not going to probably get into a ton of this right now, but we definitely will be coming back to it more and more. So this is not going to be the only time that we see this in this class. We will come back to it and apply it more and more. So make sure you kind of be able to keep track of this stuff. It's not going to go away. Put the time and effort into mastering this now. It's going to make life a whole lot easier come February and March when we're doing this and applying it. All right, so London dispersion, weakest. Okay, nonpolar molecules, dipole-dipole, or with polar molecules, the greater the difference in electronegativity, the stronger the force is going to be. And then the last one here is our hydrogen bonds. Now, this is only a specific type of polar. Okay, so this is really an extreme case of a dipole interaction. So it's a specific type of dipole. All right, so this is when you have a polar bond. Hydrogen is basically reduced to a proton. What that means is if you think about hydrogen, okay, and you write out protons, neutrons, and electrons, it's got 1 proton, 0 neutrons, and 1 electron. Now, because that this is sharing taking place in a polar bond, the other elements in this extreme case of hydrogen bonds are basically just taking the electron away from hydrogen so that it basically has none because it's a greedy sharer, the other 3 elements that this will happen with, and it's leaving it with just a proton. So that's what that means. It's got almost no atomic radius, so it's just a very extreme case of polar bonding, which makes it so strong. Okay, this is the strongest of all the IMFs by far. They only occur in molecules with the following elements. So obviously it's got to have hydrogen, and then it's got fluorine. So it's hydrogen bonded with fluorine, or hydrogen bonded with oxygen, or hydrogen bonded with nitrogen. Okay, it's only these 3, and maybe sometimes it's associated with chlorine, but for our purposes, we're not even going to worry about it. Okay, it's hydrogen bonded to fluorine, so you've got HF, you've got HO, okay, or like H2O, really, is the way you want to think about it, and then nitrogen. So if you've got nitrogen and hydrogen in the compound, so something like ammonia or something like that. Okay, we're not going to worry too much about it. So just think about those 3 elements. So the way I help you remember this, think back to what's the 3 most electronegative elements on the periodic table. Oh yeah, it's these 3. That's why we have hydrogen bonding to these, because they're the most electronegative. So remember, chem is Fon, right? F-O-N. Those 3 are the strongest. That's why they are the only ones that have hydrogen bonding. Remember, it's an extreme case of polar bonding. Okay, it's an extreme polar bond that's happening. So go back, review this. You've got a few worksheets here with IMFs to look at. There's 2 different ones that you need to work on. If you have questions, ask. Make sure you know this material. It's a lot of concepts, so you've got to put the time and effort in class as well as outside of class, meaning maybe, if you're watching this before break, you want to. If not, you definitely need to be studying when you get back so that you can do well on that summary quiz. And again, this is not going to go away. It's not staying here in this unit. We will be using it a whole lot when we get to things like kinetic molecular theory and solubility, which comes later on in the year.